Okay, so we've got these interesting functions that we've all had a little bit of time to try to tackle on our own. And based on your feedback, we will work several of them out. All right. So let's start with the square root of e to the x. Right? That was e. It was like h of x. Is that what it was? H of x is that thing, right? And I would like to find h prime of x. H prime of x equals question marks, right? How am I going to get started here? Yeah, the square root I definitely want to think of as a power. Right? This is e to the x raised to the 1/2 power. Okay. So when I take the derivative, what's that going to look like? I'm going to get something like this. So what I really have here is I have something raised to the 1/2. Right? The inside function here is e to the x. And the most basic thing that's happening in this function is that I have something raised to the 1/2. Right? I'm pretending that this e to the x is just a plain old x, and that I have x to the 1/2. So the derivative is going to be 1/2, whatever the inside function is, to the negative 1/2. E to the x to the 1/2, I'm going to differentiate just the same as I differentiate anything to the 1/2. Right? So the power comes down, the inside stays the same, the exponent is reduced by 1. But this e to the x inside is not just a plain old x, it's not just plain old anything, it changes at a different rate. So I'm going to multiply at the end here by the derivative of that inside function. And the derivative of e to the x is e to the x. So here is where everybody should get without too many problems. I'm seeing a lot of heads nod. That's encouraging. Okay. So after this, it's just algebra. There are a couple of ways to look at it, I guess. This negative exponent, for instance, you might think, oh, that means that it's going to get pushed to the bottom. So my denominator is going to have a 2 in it, 2. And it's also going to have this e to the x to the 1/2. Like that. And then there's this e to the x that is a positive exponent, so it stays on top. So if I wanted to stick with the square root notation that I started with here, I might see something like this. But I also might be thinking a couple of other things. Things like this is e to the x, this is e to the x to the 1/2, right? These are the same base. E to the x to the 1 and e to the x to the 1/2. So that's e to the x to the 1/2 over 2. I can just 1 minus a half is a half. That are anything divided by its square root is just the square root of that thing, right? 81 divided by the square root of 81 is the square root of 81. By definition, that's what it means to be a square root, right? That if you multiply that thing by itself, you get the original function. Right? So the square root of 81 is that thing that you multiply by itself to get 81. So if you divide 81 by its square root, you get its square root. Same with e to the x. So something like this, or that's root e to the x over 2, or 1/2 square root e to the x. Any of these are pretty nice. I'm kind of partial to this one, but I really like rational coefficients more than I like fractions. But that's just my own deficiency. If you don't share that with me, then that's fine. This is fine. This is fine. This might have been a little bit easier if way back here, I might have said, I have an exponential expression raised to an exponent. So this is just e to the x times 1/2, right? An exponent raised to an exponent, you can multiply. So this is e to the 1/2 x. And if I just differentiate that, Now it's e to the 1/2 x times the derivative of 1/2 x. I can use the chain rule here where the outside function is e to the something. Right, it's down here. Right? The outside function is e to the something, and then the inside function is 1/2 x. Yes?
So if it's e squared quantity cubed, it's really e to the sixth.
Yes. So e squared quantity cubed would be e to the second to the third, so you multiply e to the sixth. All right. So a little bit of algebra from the past could have saved us a little bit of trouble here, and there would have been less kind of square root business. But we would have wound up in the same place. So no big worry. Any questions about this? No? All right. Moving backwards, related to this problem, is the next question, right? D was f of x equals e to the square root x. Okay. This is like a sister problem. Before, the inside function was e to the x, and the outside function was square root of x. Here, the outside function is e to the x, and the inside function is square root of x. So they've just kind of flipped which one was the outside and which one was the inside. So here, at the most basic level, I have e to the something. The derivative should be e to the something. But then I have to multiply by the derivative of whatever that something is. So the big trick here is being able to differentiate square root of x so that I can do the second part. Remember that root x is x to the 1/2. So its derivative is going to be 1/2 x to the negative 1/2, which is 1 over 2 root x. That negative exponent pushes it to the denominator in order to be a positive exponent, and a 1/2 exponent is a square root. So really, f prime of x here is e to the square root x times the derivative of its exponent, which is 1 over 2 root x. And if I combine these into a single fraction, I get something like e to the root x over 2 root x. So even though it's involving the same two operations, the same functions, right, root x and e to the x, because of the way that I've composed the functions, the derivatives will be changing differently. Just because, I mean, the functions are different because I put them together in a different way. So the rates should also be different. Questions with D? Seems okay? Everybody feels satisfied about D? All right. Well then. A was the second most kind of confusing, according to feedback. Okay. And it's going to feel a lot like E did, right? A here is g of t equals the square root of t cubed minus t. Okay. So just like before, this is a function, t cubed minus t, raised to the 1/2 power. Right? In E, it was e to the x raised to the 1/2. In A, it's t cubed minus t raised to the 1/2. We're going to evaluate it exactly the same way. I have something to the 1/2. So the power comes down, the inside stays the same, the power is reduced by 1, okay? Just like I normally do, right? Something to the 1/2 is 1/2 something to the negative 1/2. The something is t cubed minus t here, so it's t cubed minus t here. But because t cubed minus t is more complicated than just a plain old x, I need to multiply here by the derivative of t cubed minus t, which is 3t squared minus 1. Here is a great place for everybody to be. Hopefully everybody was kind of here with no problem, maybe. Yeah. After this, it's just algebra. I'm going to notice that I have a negative exponent. I don't like that. It needs to go. Moving it to the denominator, right? It'll be a positive 1/2. The 2 is already in the denominator from this 1/2 coefficient. And the 1 is up here, and this 3t squared minus 1 is up here. Because I started off with square roots, I might try to end this with square roots. So you get something like this. 3t squared minus 1 divided by 2 square root t cubed minus t.
Can you explain the denominator one more time? Maybe we're almost there.
All right, so moving from here to here, my idea is that this negative 1/2 exponent, in order to make it positive, the base will move to the denominator and the exponent will become positive. Okay. So this entire expression, if it moves from the numerator to the denominator, then the exponent can change signs. This 2 is from the 1/2. There's already a 2 in the denominator of this expression. And then the 3t squared minus 1 is still in the numerator, and this 1 factor is still in the numerator. But 1 times anything is whatever it was to begin with. So the factor of 1 we don't have to write. Other questions? Straighten. All right. C, maybe the most kind of algebraically weird of the bunch. Okay. It was Q of R equals 1 divided by 3R minus 3/2 R cubed, the quantity squared. And the thing that I would like to do with this immediately is I don't like that it's a quotient. And since it's simple in the top, I might just move this entire denominator to the numerator by negating the exponent. So if I make this observation, it's going to make things a lot easier on me. Otherwise, I'm going to use the quotient rule, and then it's like low d high, and the low is this whole thing. And then when I do d low, it's the derivative of this whole thing, which I have to use the chain rule for. And then I have to take all of this and square it as part of the square of what's below part. There seem to be a lot more moving parts. I'd much rather just kind of think about this expression raised to a power. And then it's pretty straightforward, right? I have something raised to the -2. So to take the derivative, I bring the power down. The inside stays the same. I reduce 1 from the exponent. And then because this variable base is more complicated than just a plain old R, I have to multiply it by the derivative of that expression. Okay? So the derivative of 3R is 3, and the derivative of 3/2 R cubed, I multiply by 3, and I'll get 9/2 R squared. So here's the derivative of the inside function. Here, again, is a great place to be. The only difference between here and maybe a final solution that I might like better is that this has a negative exponent, and I might want to make that positive. So I could do something like -2, 3 minus 9/2 R squared all over 3R minus 3/2 R cubed, the quantity squared. Something like this. Not the squared, the quantity cubed. Okay. This is a -3 power, so if I move it to the bottom, it's going to be a +3 power. If I multiply this -2 in, it'll get rid of the 2 in the denominator. That might be nice. But because I already have a fraction in the denominator, I'm not going to worry about it. I'm just going to kind of leave it the way that it is. Fractions inside of fractions. There's no really nice way for me to get rid of this one, so just screw it. We'll have it complicated. Questions here? Okay. There's a familiar pattern to these types of problems that you will fall into. It might take 10 problems to work, it might take 20 problems to work, but I promise the more of these that you work, the more comfortable you'll get with the process. And you want this process to be smooth. You want it to be something that you can handle really easily.